Welcome to the University of North Georgia online version of Math 3350. This is probability and statistics. We'll be tackling probability in the first half and statistics in the second half of the course. And just to let you know the structure, each of these modules is going to have the videos, but I've provided the handouts. So you want to search and make sure you get the handout. This prints 4 slides per page, and there's room below each slide to take some notes. So you'll want to print these out and have them available as you go. Also, there's course notes, sort of the textbook for this class, and section 1 goes with module 1. So it doesn't matter which order you do this in, the videos first or the text, but you should do both of those before you take the completion quiz for the module. Okay, so getting started. We're going to take a set theoretic approach to probability. So while a lot of these probability questions you could have done on your own, let's think about the set elements and what's going on as we think about this. So probability experiments are actions whose outcomes are perfectly random and predicted exactly by probabilities. And those probability experiments include outcomes, all the possible things that can occur from the experiment. And we call the set of all outcomes the probability space S. In set theory, we often talk about the universal set and we call it U. And this is the exact same thing. We're just calling it the probability space to remind ourselves of this probability experiment that's happening. And then events are sets of outcomes in the probability space. So these are the sets, these event sets. And just like with regular sets, we're going to denote them with a capital letter. Okay, and then the probability of an event is the number of elements in the event set A divided by the number of elements in the probability space. So this is number of preferred outcomes divided by total number of outcomes. And in absolute value, the absolute value of A means the cardinality of A, or the number of elements that are in A. So when we use this absolute value notation, that's what we mean. So we are also going to take a lot of our event sets and use set operations to break them up and to deal with them more easily. So one of the most powerful probability tools is using set complements. So for an event set A complement, which we'll denote with this bar over the set, a complement are all the outcomes or elements that aren't in A. For intersections, we have A intersect B, which relates to the event where the outcomes are both in the event set A and in the event set B. We have unions. They're very powerful. It's most helpful when the event set A and B are disjoint or mutually exclusive, but we can handle it when they're not as well. So this relates to the event that the outcomes are either in event set A or in event set B. Also, we don't use this a ton, but it's important to understand it when the notation comes up. When we use A minus B, some mathematicians call this A throw away B. And what it refers to is we take all the outcomes that are in A, and then we check. And any outcomes that are in A that are also in B, we throw those away. So it's just the stuff that's in A, but not in B. Okay, so one final thing before we start doing some work here are partitions. This is one of the most powerful tools, and it's got its whole section later in the course. But we want to introduce them now so we can be talking about them and be understanding them a little better when it comes time to use them in probability problem solving. Okay, so a partition is just a collection of subsets in the probability space, and they have the following properties. None of them are empty. They're pairwise disjoint. That means that when I take, say, A1 and I intersect it with A2, that the result is the empty set, right? And this will be true whether it's A3, A4, no matter which pair of of subsets I choose, their intersection is going to be empty. And the last thing is that the union of all these subsets has to be the entire probability space. That will mean that no matter what I pick in the probability space, what outcome I pick from the probability space, I'll always be able to find it in one of these subsets. It'll be somewhere in here. I don't know which one necessarily, but I know that it'll be part of the subset, one of the subsets of the partition. So the best way to understand partitions is to think about a standard deck of 52 playing cards. And it has four partitions, it has a couple of important partitions. The first one I want to look at is the suit partition, right? So we have four suits, we have spades. The spades subset has 13 cards in it, right? And you can see them right here. These 13 cards are one subset. They all have the same suit of spades. And there are four subsets in the suit partition. We also have the hearts, ace, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, and king of hearts. Those are the 13 outcomes, or the 13 cards in the hearts subset. We also have the club subset and the diamond subset. Now, we can also think of the value or the rank of the cards. That creates a 13 subset partition, right? So we have the aces subset. So there are four aces. And we have the tens subset. There are four tens. And there are 13 of these. Here's the 7 subset, right? And so what's true, notice that they're pairwise disjoint. I'm either a 7 or a 10. I can't be both a 7 and a 10. None of these subsets is empty, right? We have 13 values and each of them has 4 cards, and the union is S. No matter what card I pick, it's going to be in one of the 13 value subsets. So that's a quick overview of partitions before we get started. When we look at probability experiments, we do want to understand what features it has, and there are a couple important ones. Are the draws with or without replacement? So when we talk about draws with replacement, that means that the sample space is unchanged from draw to draw, like when you spin a roulette wheel. When we have draws without replacement, the sample space changes from draw to draw, like when you're drawing a card, right? If we draw 5 cards into a poker hand, obviously the probability of getting an ace on the second draw is different than it is on the first draw, mainly because the denominator will be different, right? There are 52 choices when I pick the first card, but there's only 51 cards left when I pick the second card in the hand. And finally, repeated trials when we rerun the exact same experiment several times, like flipping a coin 5 times and asking how many heads occur out of the 5 coin flips. Now, one thing that's important about repeated trials is it doesn't really matter whether we flip the same coin 5 times or whether we flip 5 coins at once. We often model this with a probability tree. But we can model it whether it's sequential or simultaneous. We can model that with a probability tree either way. And we call this Bernoulli trials. And the cool thing is that the binomial theorem is a perfect model for the situation. It's actually a really powerful problem solving tool. Again, we'll have a whole section devoted to it later in the course. So I wanted to highlight that for you now. So when we're trying to calculate these probabilities, since it just comes up to counting all the outcomes in A and counting all the outcomes in the probability space, so efficient counting techniques will be very important. I'm not going to dwell on this. I want to do some probability calculations for you here using the set theory. So just quickly, we have permutations. These are draws without replacement where the order in which the items are drawn matters. And we have combinations where there are also draws without replacement and the order doesn't matter. And we have Cartesian products. Now these are draws with replacement, and Cartesian products, I am actually trying to get you to think of, things from the, Cartesian coordinate plane, x comma y, right? So x comma y, these are elements of the real numbers, and I don't think that's going to fit. The real numbers, oops, that's r squared. The real numbers cross, that's not real, didn't quite make it, cross the reals there. And what this means, if you can see, it's I pick a real number, and that's my x, and I pick another real number, and that's my y. And so the number, the cardinality of the Cartesian products is the number of elements in the first set times the number of elements in the second set. And we use this pattern all the time in our probability calculations. All right. So now I believe we're ready to do some calculations. But let's go back to the standard deck of playing cards, and we're going to identify some more partitions, some more subsets. So first of all, each card has a 2-character code. Now these were invented by poker players, but if I use the value partition notation, right, plus a lowercase letter to indicate the suit. So 7H is the 7 of hearts, and 10D is the 10 of diamonds. Now, it's important if we use the 10 as in 10, if we used its numeric code, it has 2 symbols. If we use T for 10, then every one of these cards will have a 2-character code that we can identify it by. All right, and so here's the full deck in algebraic notation. So you can see how that would look. And so what we're going to do here is we already have the subsets that we mentioned. These are the suit. This is the suit partition. We have the value partition, and let's just name a few more. So inside the deck we have red and black. So red is the union of the hearts and the diamonds, right? Hearts and diamonds. Black is the union of the spades and the clubs. So there are 26 red cards. There are 26 black cards. So red and black is also a partition. It's a 2 subset partition. We have face cards. So face cards and non-face cards would be a partition, and the face cards are the kings, the queens, and the jacks. Aces don't have faces. This is just 12 cards, 3 values. And the last ones we'll take a look at are evens and odds. So when they're numbers like 2, 4, and 6, telling that they're even is okay. But what do we mean by even when we get to the face cards? Well, we'll just continue the pattern, right? So we skip the 9s and get to the 10s. Let's skip the jack and get to the queen. So the queen will be even. And the jacks and the kings will be odd. So the female face card, the queen, is even, and the 2 male face cards, jack and king, are odd. So let's look at drawing a single card at random from a standard deck of playing cards. And the first question is, what is the well, let's look at the event set, not drawing a heart. Okay, so for all these examples, we're going to put them in set notation. So this is the probability of not drawing a heart, right? So we're using the notation for the complement of the set H. And the probability of the complement, this is just like the probability of it not raining. If the chance of rain today is 40%, the probability that it doesn't rain is 60%. So we're just taking 1 minus the probability of H. Well, the hearts have 13 cards in them, right? So this probability is 1 minus 13 over 52. And I'm struggle bussing here, which is going to be 39 over 52, which is 3/4, which makes sense. I have a 1/4 chance of drawing a heart. So I have a 3/4 chance of not drawing a heart. So drawing a non-king red card, okay, let's think about the set version of that. So this is the probability of red intersect K complement, or red throw away K, however you'd like to think of it. And since there are 26 red cards, and 2 of those red cards are king, we can throw away the 2 from the 26, and we get 24 over 52 is the probability there. So 24, and that will reduce to 6/13. Okay, so what about drawing a red king? All right, well now we're talking about the intersection of all the red cards and all the kings. Okay, well there are 4 kings. It's a pretty small set, and half of them are red. So now we're talking about the probability being 2 over 52 or 1 over 26. All right, so the key here is just being able to make sure that we're mapping correctly between the words, the text, and the set notation, set operations that will give us the equivalent statement. So what's the probability of not drawing an even or a diamond? Okay, so that's the probability of, that's the complement of E union D, right? We can count up all the cards that are even, and put that together with all the cards that are diamonds, and count up everything, and then do 1 minus that. Okay, so let's just think about this. So the even cards, there are 6 even cards in every suit. There's 6 even and 7 odds. Remember, because the queen is even, but then the king and the jack are odd. So we only have 6 times 4. We have 24 even cards. Okay, and then we're going to add all the odd diamonds to it, right? So with all the even diamonds already there, but we need to add the odd ones in. So that's 7 more cards. So we have the 24 plus the 7, so we have 31. So the probability here is going to be 1 minus 31 over 52. Okay. And again, the key is being able to understand all this set notation and how it translates into operations that we can work with in these probability settings. Okay, so let's jump forward. The next example is drawing either an odd card or a face card. Okay, so there are 7 times 4 odd cards, so that's 28. And since we're talking about odds, we already have the kings and the jacks, but if we're going to add the rest of the face cards, we would have to add the queens, right? So now we have 8 times 4, that's 32. So 32 over 52 is this probability. What about drawing a card that is male or red or even? Okay, so let's try to get this. If we count up how many red cards there are, right? That's half the deck. That's 26. And then we need all the black even cards, right? So all the even cards that haven't been counted yet, those will be the black even ones. Well, there are 6 even cards per suit, so we have 12 more that are black evens. Okay. And the males are odd, remember. So now we have all the red cards, all the even cards that aren't red, which are all the black even cards. And so now all we need are the black male cards. So those are going to be the kings and the jacks that are black. So there are 4 outcomes here. So you can see that we have 42 outcomes over 52. So this is 42 over 52, which reduces to 21 over 26. What's the probability that we draw a card that is red and it's even and it's not a 6? Okay, red and even and not a 6. So we can go through the same way and start counting up these sets. So not a 6, if we do even but not a 6, then we're going to have only 5 even cards per suit. So there are going to be 20 even cards if we eliminate the 6, right? So now we have to get all the red cards that are not counted yet, which will be all the odd red cards. There are 7 odd cards per suit, 2 suits that are red, so this should be 14. So we have 34 outcomes divided by 52, or 17 over 26 is our probability there. Now this is interesting. This actually uses De Morgan's laws, so I'm going to try to remind you of that. Right? So remember, De Morgan's says that if we have the intersection of complements, that corresponds to the complement of unions, all right? So when we try to split this set complement over various sets, it flips unions to intersections and vice versa. So if you aren't familiar with De Morgan's laws, now would be a good time to pause the video and go check that out. And let's just talk about this probability. Drawing a card that is not red, not odd, and not a face card. Okay. It's not red, it's not odd, and it's not a face card. Well, one thing that we could do is we could count up how many red cards there are, how many odd cards there are, and the face cards, and subtract from 1, right? It's going to be a lot easier to work with the set complement, which is why it's important to understand the De Morgan's laws so that we can calculate the right thing here. So how many red cards are there? There are 26 red cards. Odd, well, we have to add the 7 spades odd cards and the 7 clubs odd cards, so there are 14 more that are odd. So remember, the kings and jacks are odd, and so all we have to worry about are the 2 black queens over here. Those are the only things that haven't been counted in these previous sets. So once again, I have 42, or I have 42 things in my outcome, so this probability is going to be 1 minus 42 over 52. So the final thing we want to look at is the principle of inclusion-exclusion. So we have this formula for, in general, when we have sets A and B, the probability of A union B is the probability of event set A plus the probability of event set B minus the intersection. And let's switch over to the iPad to see why. All right, so if I draw event set A and event set B, right, when I take the probability of A union B, the first part, when I take the probability of A, I am getting this intersection counted once. And when I take the probability of B, I'm counting this intersection again, right? So it's been counted twice. So that's why we have this subtraction term minus the probability of A intersect B. Okay, so hopefully that explains the formula. So, but what happens when we have more than just 2 set intersections that are possible? And that's called the principle of inclusion-exclusion. And it describes how these intersections interact when we have multiple event sets. So let's take a look at it for the 3 set case, right? We're looking at this part and then questioning kind of what happens afterwards. And again, you'll understand why it's called inclusion-exclusion in just a moment. Okay, so let's draw our event sets. All right. And we have event set A and event set B and event set C. Okay, so when we do the probability of A union B union C, probability of A gets this set intersection right here, gets all of these, right? It gets these right here. Okay, plus the probability of B, right? And let's switch our highlighter color. And so then B gets all of these intersections, right? Then when we do the probability of C, we are getting these intersections here. Right? So now what happens? Well, we've added these intersection areas. Well, let's count. Um, so we've added this one twice, right? When we did probability of A, and then again when we did probability of B. We've added this one twice when we did the probability of A and when we did the probability of C. And we've added this one twice, probability of B and probability of C. Both included that two-way intersection. But how many times has this piece here in the center been counted, right? Well, that was in the probability of A. It's also in the probability of B. It's also in the probability of C. So now that three-way interaction, that three-way intersection has been counted 3 times. So what we're going to do is going to look very similar to what we did before. We are going to subtract the two-way intersection. So I'm going to subtract P probability of A intersect B, and I'm also going to subtract the probability of A intersect C, and finally I'm going to subtract the probability of B intersect C. Okay, so now what's happened? All right, so let's take a look at this, right? So when I subtract A intersect B, I've gotten rid of one of these two, and then when I subtract B intersect C, I've gotten rid of it, right? So at the end of this, this one's gone, right? Same thing. I'll get rid of one of these when I do A intersect C. Wait, I'm sorry. There'll be one left, which is what I need, right? There's one left here and there's one left here. And same thing when I do B intersect C, I'll get rid of one of these, right? And they'll be added in one time like they're supposed to be. That was the point. But what's happened here? This one in the center has been added 3 times, right? One each here, right? But it's also been subtracted 3 times for each of the intersections it went out. So there's no more of the middle intersection. So what do we have to do? Well, we're going to add the three-way intersection. Probability of A intersect B intersect C has to get added back in. And this is what we mean by inclusion-exclusion. So we first include all the probabilities of the sets. We just add them. Then we subtract all the two-way intersections, right? So the two-way intersections, right? We first do the probabilities of the sets themselves, right? And then we do the two-way intersection, subtracting each possible two-way intersection. And then we add in all the three-way intersections, and this can continue for 4, 5, and 6 sets, right? We would just then, after adding in all the three-way intersections, we'd subtract out all the four-way intersections and then add back in all the five-way intersections, and you can see the pattern. I hope also that this helps explain why we much prefer the situation where we have disjoint event sets, right, as in a partition. Because when we have disjoint event sets, their probability here, the probability of A union B union C is just the probability of A plus the probability of B plus the probability of C. There's no inclusion-exclusion. That's why we really love partitions. They'll allow us to sum things up very easily without having to use inclusion-exclusion. Remember to look at the text, the course notes, and do the completion quiz. Good luck.